CBSE.com. This is here Joyce. Now today we are going to prove the irrationality of a number. Class 10 Math, Real Numbers, NCERT. Are you all ready? Shall we start? Here we go. Children, we are going to prove the rationality or the irrationality of a number. You know, the rationality means the number can be expressed in the form P by Q, where P and Q are the co-primes and Q not equal to 0, or P and Q are the integers also, of course. So, that rationality we know, but what is about irrationality? Irrational number means which cannot be expressed in the form P by Q, where P and Q must be an integer, but we cannot express in that form. That number is said to be the irrational number. Now, we have studied all these, the first subtitles of this chapter. So, by this time, you must be knowing about the numbers, the rationality and the irrationality. Even though, so I give the number, for example, root 2. Root 2, if this is an irrational number, I should know to write it in the form A by B or P by Q, where A and B are the integers and B not equal to 0. But I can write this number as root 2 by 1, where root 2 is not an integer. That's why I say that root 2 is an irrational number. Now, we have to prove that with the proof how this root 2 is an irrational number. Shall we go on for the proof? Prove that root 2 is irrational. So, how do we prove root 2 is irrational? Now, you must be knowing by this, all these years that you have studied math in 9th standard, you know how to prove the theorem. So, when the statement is given, how to prove the theorem. On another way, we take the contradiction, especially in the chapter circles. So, in circles chapter, to prove whether the tangent is perpendicular or the perpendicular lies passes through the center, that is, we proved in the concept of contradiction. So, we assume some contradiction and we finally come to a result. Our contradiction, what we have taken, is wrong. So, what it is given, it is correct. That's what we are going to prove in this video. Now, I have to prove root 2 is irrational. Prove that root 2 is irrational. So, what am I going to do? I'm going to do, suppose root 2 is rational. So, I'm taking, suppose root 2 is rational. That is, we are assuming the contradiction. So, if it is rational, I should know to write this in the form A by B, where A and B are co-primes such that, what do you mean by the co-primes? They have HCF as the number only 1. So, the HCF of A and B is just a number 1 and B not equal to 0. This is what the condition, since I can express root 2 as A by B. Now, can I take root 2B is equal to A and squaring on both the sides? Can I have 2B square is equal to A square? I'm just squaring on both the sides of this equation. Now, you can see here 2 is a factor of A square. We know the theorem. Before going to the theorem statement, I want everyone to understand this concept. Suppose I have any prime number. Suppose my prime number is 5. If this number 5 divides A square, now I take the number 100, which is nothing but A square. What is A square? That is, it is 10 square. So, 5 divides A square. That implies 5 divides this A also. Of course, 5 divides 10. If 5 divides 100, that is A square, surely 5 divides A, which is 10. So, this is a theorem. If P is a prime number and P divides A square, then P also divides A. Because of that, I can say here 2 divides a square implies 2 divides a also. So when 2 is dividing a, I can write a divided by 2 is equal to some integer. That is, dividing means what? We get a quotient. So to divide this a means I am going to get a quotient. So that is equal to c. Now how can I write this as? That is a is equal to 2c. Now I am going to take the square on both the sides. It will have a square is equal to 4c square. Now you can see in this first equation, I already have a square is equal to 2b square. So let me substitute a square is equal to 2b square. Substitute 1 in this second equation. In 2 I substitute. So I get it 2b square is equal to 4c square. That gets cancelled. So b square is equal to 2c square. That means what? B square has the factor 2 also, and a square has the factor 2 also. But what we have assumed here, a and b, the highest common factor is just the number 1. But I am getting 2 as the another highest common factor for these two numbers, a and b, which is a contradiction to our assumption. So I say which is the contradiction that implies my root 2 is irrational. Hope everyone get my point how to prove it is irrational. That is, root 2 is rational. I take our root 2 is equal to a by b, and because of this theorem, I prove that there is one more common factor for both a and b, which contradicts to our assumption such that a and b has the common factor only the number 1. But this is a contradiction to our assumption what we have taken. So root 2 is irrational. Hope everyone understand this concept, how to prove root 2 is irrational. Similarly, children, we would be proving root 3, root 5, root 7, all these are the same concept. For your understanding, let me prove root 3 also. So now children, we prove root 3 is irrational. So how do we prove? We take, suppose root 3 is rational. So what I would do, I would be able to write root 3 as a by b, where a and b are co-primes and the highest common factor HCF of a and b is 1 and b not equal to 0. So now I have root 3b is equal to a. So squaring on both the sides, 3b square is equal to a square. That means 3 divides a square implies 3 divides a also. So that means a divided by 3 is equal to some integer. A is equal to 3c. Squaring on both the sides, a square is equal to 9c square. Now I have this equation 1 and 2. So because of 1 and 2 implies I would have 3b square is equal to 9c square, which gets cancelled. So b square is equal to 3c square. Children, this implies b square is equal to 3c square. That means 3 divides b square implies 3 divides b, which is the contradiction to our assumption a and b have the highest common factor 3 also. Not only a and b, the highest common factor of a and b is 3 also, which is a contradiction. So that is not possible. Therefore, root 3 is irrational. As simple as that. Hope everyone understood how we proved. So HCF of a and b is 3 also. That is a contradiction. So root 3 is irrational. Shall we move on to the next proof? Children, we move on to the next proof. Prove that 3 root 2 is irrational. Suppose we take 3 root 2 is rational. So the same way we prove it. So that becomes 3 root 2 is equal to some a by b. That implies root 2 is equal to a by 3b. So this is a rational number. That implies root 2 is rational. But we already proved root 2 is not irrational, which is a contradiction to our proof, that root 2 is irrational. So I can say that that implies 3 root 2 is irrational. As simple as that. We prove the theorem. That's it. We move on to the next proof. Children, prove that 3 plus 2 root 5 is irrational. So how do we prove it? Suppose 3 plus 2 root 5 is rational. So what I would take? If it is rational, 3 plus 2 root 5 is equal to a by b. So I would have 2 root 5 is equal to a by b minus 3, which is equal to a minus 3b divided by b. So that is equal to 2 root 5. So my root 5 is equal to a minus 3b divided by 2b. You know that this is rational. Why? Because this all includes integers. That implies root 5 is rational. But we know that root 5 is not rational, which is a contradiction. So that implies root 5 is irrational, and the given number 3 plus 2 root 5 is also irrational. So hence true. Children, now we see this question. There is no positive integer n for which root n minus 1 plus root n plus 1 is rational. Now what is this, ma'am? It comes in under root and the n. How do we understand? Now I'll give an example. Suppose n is equal to 5. So I've taken, there is no positive integer. So let me have my positive integer is 5. So when I substitute 5 minus 4 plus 5 plus 1, which is equal to root 4 plus root 6, which is equal to 2 plus root 6. Now, since we have done the previous question, you understand any irrational number is added or subtracted with the rational number, the result is going to be irrational. Now, this is what the result, any positive integer if you take, that is going to be irrational. That's what the question says. You cannot prove for any positive integer the result is rational. You cannot prove it. So, but we'll try to see whether that statement is correct. So, how do we prove it? So, let me have this as suppose rational. This is irrational. That's the meaning of this question. Now, I take suppose root n minus 1 plus root n plus 1 is rational. So what happens when it is rational? I would be able to write plus root n plus 1 as a by b. Now to prove my rationality, what I do, I just take the reciprocal. So that becomes 1 by root n minus 1 plus root n plus 1. Now what I do, I take the conjugate and multiply the top and the bottom. So 1 by root n minus 1 plus root n plus 1 into square root of n minus 1 minus root n plus 1 divided by root n minus 1 minus root n plus 1, which is equal to b by a. Now this becomes a square, a plus b into a minus b. So my numerator become root n minus 1 minus root n plus 1 whole thing divided by a square, that is n minus 1 minus b square, that is n plus 1, which is equal to b by a. Let me simplify further. So root n minus 1 minus n plus 1 divided by n minus this minus n plus n gets cancelled. So I get minus 2, which is equal to my b by a. So now I take my minus to the top. So that becomes n plus 1 minus root n minus 1 divided by 2, which is equal to b by a. Now I take this equation as my second equation and this equation my first equation. So now I will add 1 and 2 equations. So 1 plus 2 implies a by b plus 2b by a is equal to, when I add these numbers, this and this gets cancelled. So I'm left with 2 root of n plus 1. And I further simplify this, a square plus 2b square divided by ab is equal to 2 root n plus 1. This is by adding. Now I am going to subtract 1 and 2. So 1 minus 2, when I do, I get cancel of these two. So I would get a by b minus 2b by a is equal to root n minus 1 plus root n minus 1. That becomes 2 times root n minus 1. On further simplification, a square minus 2b square divided by ab is equal to 2 root of n minus 1. So I get, when I add and I subtract, I get these two equations. Now children, what I do is a square plus 2b square divided by 2ab is equal to root of n plus 1, and here I am getting a square minus 2b square by 2ab is equal to root of n minus 1. Now this is an integer. This is an integer. That means this is going to be an integer. This is going to be an integer. When the square root of any number becomes integer, when the inside the square root, the square, perfect square number is there, then the result will become an integer. So n plus 1 and n minus 1 are the perfect square numbers. So children, n plus 1 and n minus 1 are rationals. Why? Because left hand side is rational of these two expressions. So right hand side automatically becomes rational. But when it is rational, surely it means n plus 1 and n minus 1 are the perfect square numbers. You should understand from the concept. So perfect square numbers. What are the perfect square numbers? Perfect square numbers, when you take the difference between any two perfect square number must be minimum 3. Why? Because the perfect square, the smallest perfect square number is 1 and the immediate perfect square number is 2 square, which is 4. That is 4 minus 1, minimum is 3. That means I should get the difference between these two numbers minimum 3 or more than 3. So n plus 1 minus of n minus 1 get cancelled, but the answer I am getting 2, which is impossible, not possible at all, which is not possible. That implies what I consider the given number is rational is a contradiction. So it cannot be rational. It is irrational number. So we cannot find, this implies I would write root n minus 1 plus root n plus 1 as irrational. That means I cannot find any positive integer such that root n minus 1 plus root n plus 1 is a rational number. Hence the proof. So I got this proof. Children, now we are going to see the next subtitle, Nature of Decimal Expansion of Rational Number. Please consider these numbers. And in these numbers, how the decimal expansions will be for these numbers. Of course, these are all rational numbers. Now, I would say just by looking at this is non-terminating recurring. This is going to be terminating, and this also going to be terminating, and this also going to be terminating, and this is non-terminating recurring. Now, how can we say just by looking at the number whether the decimal expansion is terminating or non-terminating recurring? How can we say that? That is what you please observe this number. This number, the denominator, the factors are 1 into 7. And here the factors are 2 into 5. And here factors are 2 into 2 into 5. And this one 5 divided by 2 into 2 into 2. And this one 19 by 3 into 3. Now I told you these two are non-terminating recurring, and these are all terminating. What is the difference between this number and these three numbers with this number? You can see here this number having the decimal expansion terminating because the denominators having the factors only the number 2 and 5. You can see here 2 and 5. Just the number 2 also it's possible. So, but when the denominator is not having either 2 or 5 or both, then we can say that that fraction, that rational number is non-terminating recurring. Otherwise, if the denominator, the factors are consisting of prime numbers 2 or 5 or both, so we say that this rational number is terminating decimal expansion. So hope everyone understand by this. Because of this, we have the theorem. So the theorem says, if let x is equal to p by q be a rational number such that the prime factorization of q is equal to 2 power m into 5 power n, where m and n are the non-negative integers, then this x has the terminating decimal expansion. So this is the theorem. So when x is equal to p by q and it is a rational number, if the denominator q has the decimal, the prime factorization in such a way that 2 power m into 5 power n is equal to q, then that x will have terminating decimal expansion. Now, shall we move on to the question just by looking at the question whether to conclude it is terminating or non-terminating recurring. Are you all ready? Children, find the decimal expansion of all these numbers, the rational numbers. Now, I'm going to get my prime factorization. This is 2q. So, this can be written as 5 power 0. So, 2 power m into 5 power n, where n is 0. That's okay, but I have to get my decimal expansion. So, what I would do, I would just multiply and divide by the same power of 2 with the number 5. So, that becomes 7 into 125 divided by 1000. That's equal to 7 5s are 35, 3 7 2s are 14, 17 1, and then 875 divided by 1000, which is equal to 0.875. So, to get the decimal expansion, how do we do our calculation? Now, the next number I would have 189 divided by 5 power 3. So, to get my decimal expansion, I would just multiply and divide by the number 2 with the same power of 5. So, I would have 189 into 8 divided by, this is again 5 cube into 2 cube, that becomes 1000, that's equal to 8 9s are 72. So, 7, 8 8s are 64, 64 plus 7 is 71, 7, that is divided by 1000, which is equal to 1.512. We'll go with the next number, that is 49 divided by, this is 2 square into 5 cube, which is equal to 49 divided by 2 square. I should have the same power, so 2 cube into 5 cube into 2, so that is 98 divided by 1000, which is equal to 0.098, as simple as that. Now this prime factorization, I would have 2139 divided by 2 into 5 raised to 4. So I must multiply this by 2 power 3 into 2 power 3, that's equal to 2139 into 8 divided by 1, 2, 3, 4 zeros. 3 power means 3 zeros, 4 power means 4 zeros, that's equal to 8 9s are 72, 7, 8 3s are 24, 24 plus 7 is 31, 3, 8 1s are 8, 8 plus 3 is 11, 1, 2 8s are 16, 16 plus 1 is 17 divided by 10,000, that's equal to 4 decimal places, 1.7112 is the decimal expansion. As simple as that. So children, we have come to the end of our chapter, Real Numbers. We'll meet in the next video with the next set of concept in the next chapter. Until then, take care. Bye-bye.